Where's my slicer? Sure, that would almost this. Projects. Let's get this one. So we have to start. Skip this. Stop. It looks as if we I don't know, my question too is trying to confuse me. So let me wait for maybe I don't know the number of students in this class. So we wait for maybe 10 minutes or so, then we start. Because we are just four of us here at the moment. So we need a critical mass before we can start. You need a quorum in order to start. But then time too is an issue, and a student. Oh no. Okay, so. Good morning, everybody. Good morning once
Good
again.
morning, sir.
Yeah, so let's start today's lecture. I have two sets of slides. When we are done, we go. So whenever we finish, we close. Um, the, then we shall be left with one slide. I don't know where I don't know when we are going to meet and then discuss that. So let's see. So I'll use maybe less than 1 hour to go through this. Then we go away. Then we go to the next slide. Where is this? So let's start from current slide, soil forming factors. Soil forming factors. Who can help me when we say soil forming factors? Soil forming factors. What is it? Anybody can answer, please.
Sir, things that lead to the formation of soils.
Yeah, things that lead to formation of soils. Thank you very much. So let me run through some of the factors. The first one that we all know is climate. Climate is very, very important factor. And when we say climate has a wide range of variables that can contribute to formation of soil. The most important ones are rainfall and then temperature. In the global north, where you have snow, glacier contribute to a lot of soil formation. So climate is very, very important. So you can look at wide range like evapotranspiration, temperature, humidity, all these factors can interact and contribute to soil formation. Then living organism. When we say living organism, we can look at man as one of the factors. Then we can also look at plants, microorganisms. The most important ones are the microorganisms. A man can also be an engineer if he can contribute to formation or destruction of soil. So so I say we are the dominant living organism that contribute to soil formation. Then the parent material determine the rate at which the soil can be formed. Soil formation from a very hard rock would take a long time in order to be formed. But then if you the soil is formed from a material like sedimentary rocks and then metamorphic, well, they are not so hard as compared to igneous rock. The parent material is very, very important. And then the parent material determines the kind of chemical composition that will reflect in the nature of the soil. Then we also can talk about relief or topography. And this is very, very important. Most often on the hilly surfaces, soil formation is very, very slow as compared to the base because of erosion. Agent of erosion will move the soil from the top to the bottom. So you have more or less soil accumulation at the base of any mountain. So this contributes to soil formation. Then we can also talk about time. Time is very, very important factor. We can describe the soil as being young or old soil. And the other time I said that if you look at soil as a resource and you classify it as under renewable or non-renewable, you fall between both renewable and non-renewable because its formation normally go beyond the our life, what do you call it? One generation. It can take maybe 1,000 years to form a soil. So soil is very, very important. Time is very, very important. factor in soil formation. Then human influence. Human influence, we can aggregate that under living organism. Living organism is also an important factor. So human influence can be part of the living organism, as I said earlier on. So these are the factors. I think there is something, I don't know whether I skip it. There is, okay, sometimes this can be represented in the form of equation. You know, soil formation is a function of all those um, factors that I've mentioned. Now, one of the important attributes of soil is the soil texture. Is the soil texture. That is basically falls under what we call the physical property of soil. Soil texture. How do you determine the soil texture? Sometimes when the soil is very moist and you feel it in your palm, you can determine whether it's a sandy or loamy or clay soil. And basically, when we say soil texture, we are referring to the fineness or coarseness of what? Mineral particles of the soil. Of course, in some textbooks, they'll say it is also the relative proportion of sand, silt, and clay. And as we move along, you realize that most of the soil chemical reaction takes place between those two components, silt and clay. Most of the soil chemical reaction occurs within the sites of silt and clay particles. So soil that lacks great proportion of silt and clay, in most cases, is not fertile. So if you have a sandy soil, obviously, sandy soil has a limitation and it is not able to support plants as compared to soil that has a relative high proportion of silt and clay. And when you have these two components in high proportion, usually the soil is described as loamy soil. And loamy soils are very good for agriculture. So let's move on. Now, when it comes to soil textural classification, we have a wide range of classification systems out there. We have a FAO classification system. We have the what they call the Bremen classification system, which is peculiar to Ghana. Then we also have USCS, MIT, and BSI classification system. So the soil textural classification system usually look at the sizes of the particles that constitute the soil. So if, for instance, if you take 2.0 to 0.2 millimeters under the TIS system, we can describe the texture as being coarse sand. Then when you move down, the size, particle sizes become smaller, and you realize that clay is below 0.002. Now, when we come, if you look at USCX, is almost equivalent to that of TIS. Then MIT is below this 0.02, 0.002. So these are the basic types of classification that we have. So let's see. But usually, let me define those terms so that you are. So the TIS is a transformation interface soil layer. That is TIS. Then we have USCS is Unified Soil Classification System. Then we have the Massachusetts Institute of Technology and the British Standard Institution. They also have their own classification. Now, the most commonly used soil textural classification is the USDA, United States Department of Agriculture system, is most commonly used classification. But when you go to the developing countries like Ghana, we also have another form of classification, and that usually follows the nomenclature of FAO. So very coarse sand falls between 2.0 to 1.0, and that is a very coarse sand. Then coarse sand is, the range is 1.0 to 0.5 in that order. And clay is the smallest clay. And usually, if you have clay in water, it forms suspension. It doesn't settle. When you mix clay with water, the color of the clay reflect the color of the water, and it's usually it become coloring. You know, so the color matrix of any soil is determined by the clay, and of course, sometimes the salt particle portion of the soil. So, soil textural classics. There are three raw soil textural classics are recognized. We have sand and loamy clays. The sand includes all soils with the sand separates, or meaning that the particles making up about 70% or more of the material mass. So if you have a soil that contains um, a high proportion of dust, then of soil particles, of sand particles, then it constitutes, or we describe it as a sandy soil, if it is about 70% or more. Then also, the most commonly recognized class in this group are sandy and loam, the meaning that most often you have a relative low proportion of clay. If uh, the salt is very high, and then if the salt is very high and low, very high, and then with relative low proportion of clay, the soil is, as I said, is usually described as loamy soil. And this type of soils are very, very fertile for agriculture. So clay soil is a soil which contains at least 35% clay, and in most cases, not less than 40% clay, and not more than 40% silt, and not less than 45% sand. So these proportions are very, very important to determine whether you are dealing with a clay soil or a sandy soil or loamy soil. So we are saying that as long as clay constitutes 40% or more, its characteristics predominate, and the class name is either sandy clay, silt clay, or clay soil. So the soil particle that is high in proportion determine reflect its characteristic most often, and that determines the name that we usually give to the soil type that we are dealing with. So let's see. So this is basically what we call textural triangle, and you realize that on this surface of the triangle, we are dealing with the proportions of clay. Here talks about silt, and here talks about sand. Depending on the location that one finds itself, will reflect on the characteristics of the soil that we have to describe. So if you have about 60% silt, if you fall about this section, and you have about 30% clay, and relative low proportion of if you have about 60% of silt and let's say 30% of sand and relative low proportion of clay, then you are dealing with silty clay loam soil. So if you find yourself in this location, you have high proportion of what they call it, silt. Now let's watch this. So if you come this way, as you move along this direction, you realize that the proportion of sand increases. The sand is almost 100% here. And when you move along this direction, you have high proportion of clay. So if you have about 70% of sand, in the proportion of soil material, then you are dealing with what? Sandy loam. When you come to this session whereby the the sand is about 10%, you realize you have a silt. More or less, you are dealing with silt. Then if you find yourself somewhere here, then you have, in this case, you have about 10% clay, then relatively high proportion of silt, then you are dealing with the loamy soil. So depending on the location within the cells that we have within the triangle, that determines the nature of the soil that you'll be dealing with. There's another concept we call soil consistency. Soil consistency in soil science. And this is the degree of cohesion of soil and it's resistant to deformation when whacked, or it's resistant to insection of an instrument like Cadillacs, shovel, knife, hoe. Is a measure of its what? Consistency. What it means that if you are able to insert the degree to which you can freely insert or material or push material through the soil measures what? Its consistency. So and it is very, very important factor when it comes to plowing. When you want to plow a soil, you need to determine those type of uh, uh, factor. If you don't determine it, it helps also as to how to, the amount of fuel that the tractor will use. Because if you are dealing with soil with high consistency, plowing becomes difficult. It means that you need more energy in order to plow. And if you are using a manual labor like hoes and you are digging in the soil and you have soil with a high consistency, it is very difficult to till it. The tilling becomes very, very difficult. Particularly when it is very wet, it becomes plastic and sticky and difficult to work with. And usually soil with high consistency is also a reflection of the amount of soil particles that I have. If you have a high clay material, that it means that the soil will also exhibit high consistency. And then working with it becomes very difficult. It's not friable, so it becomes. So depending on whether the soil is dry or moist or wet, this factor depends on this component, whether it's dry, moist, or wet. Soil are most resistant to physical force or pressure when dry. They are usually characterized by rigidity and brittleness. When we say something is brittle, meaning that it can be easily broken. It's not very, uh, that it has a less tensile strength to resist deformation. So you can just easily pulverize it into powder, or angular fragmentation when is subjected to pressure. So when soil is in a dry state, its consistency is described as loose, soft, slightly hard, hard, very hard, extremely very hard. And that would depend, as I said earlier, on the texture of the soil. The texture of the soil. In most cases, clay soils, when they are dry, they are very, very difficult to work with. They become very, very hard, clay soil. And when they are wet too, they become sticky. So, and that reflects on the nature of its consistency. So let's say the consistency of moist soil is described as loose, very friable, firm, very firm, or extremely firm. Okay. So loamy soils are usually friable. They are very easy to work with when even wet. You can easily use instruments or implement in them, unlike clay soil. So wet soil is usually sticky. They can stick to other objects, and plastic. That is, they can be pressed into any shape without breaking and can retain the shape on release of external pressure. So that's one attribute of wet soil. So let's move on. Then another thing I mentioned the other time is the soil structure. Soil structure. Soil structure is very, very important component that determines how air, water can move through the soil. And soil structure has a direct relationship with the level of organic material that you have in the soil. So the sand and clay particles of the soil are cemented together in the soil to form natural units of compound particles or aggregates, separated by pores, cracks, or planes of weakness. And this is sometimes described as the soil. It's the aggregation, to put it in a simple way, the aggregation of soil particles together is described as a soil structure. So the term structure is used to describe arrangement of the primary particles into natural aggregates or pets. And this pet comes in various shapes, and we shall talk about them. So when you till the soil and they form lumps. The shape of the lumps will determine the kind of the soil structure you are dealing with. So the structural units of four principal types are flats. You may have a soil lumps that are in the shape of flat or platy. Then you can also have a shape like prism, a block, or many-sided, more or less round or spheroid. You can also, so let's look at this. So these are the what do you call it? The pictures of some of the soil structure. So these are the crumbs that I'm talking about. If you look at this one, this is blocky, and this is in the form of a plate. So usually we described it as being a platy. Then the crumb or granular form. The granular forms are normally smooth in nature. Then you have something like this. These are prismatic, and sometimes we describe them as the spheroid. So these are the pictures that we have for these types of aggregates that we've mentioned so far. Then there is another concept in soil called soil density and porosity. Soil density and porosity. Soil density. So particle density is defined as the mass of a unit of volume of soil solid, usually expressed in gram per cubic centimeters. And then I will ask you to go and then do a little bit of research on soil density. Why is it so important to know the soil density? Of course, porosity talks about uh, the relative pores we have within the soil metrics. So let's say a bulk density or apparent specific gravity is mass of unit volume of soil measured in gram centimeter gram per cubic centimeters. It is measured using oven dry soil sample of a mass W and a volume V. Now, soils usually with high bulk density. With high bulk density, it means that if the soil has a high bulk density, or what it means is that the holes in that soil are very, very, very small. So there is a relationship between bulk density and porosity. So soil that are so compacted has high bulk density and has low porosity. So if a soil has high bulk density, it means that it also has what? Low porosity. And when these two parameters occur together, it means that the movement of water and air through such a soil becomes a difficult scenario. So let's look at mathematically, we can write the bulk density as W. That's the weight of the dry mass of a soil and the dry volume of that soil. Then we can also, this talked about the laboratory steps that you need to take. Often when you have a soil from the field, you can um, weigh it. Then when you put it in an oven, it also gives you another weight. So this the difference between these two weights will give you the actual weight of the soil. Because when you have a soil from the soil, it contains water, you have air in within the pulse, and all this can contribute to the weight. Normally, we put them in the oven to dry them, and after that, we compute the volume in order to estimate the bulk density of the soil. So this should be done in a laboratory for everybody to see. And the nature of our course is said that we it's online. So I don't know how. So if you have time, you can Google or go to the YouTube. You may have somebody who is performing this experiment, so that you can learn from such an individual. So soil porosity, the pore space of a soil is that portion of a soil occupied by air and water. It is its amount is determined largely by the arrangement of the soil particles within the soil. And this parameter is very, very, very important in every soil. As I said earlier, well, it has a relationship between bulk density. So soils with high bulk density usually tend to have relatively small porosity. So the percentage pore space is calculated from the following equation. So as I said, it has something to do with the bulk density. So you realize that we have the bulk density times 100 divided by particle density. When you subtract that from 100, that gives you the pore space. So the higher the bulk density, if the bulk density is very high, it means that pore space will be affected. So let's look at the score, the soil color. The soil color is usually as a reflection, it has a reflection of the kind of organic material, then the mineral component of the soil itself or the parent material. Darker soil or black soil usually has higher proportion of dead material. So the color of the soil is an important diagnostic tool widely used to describe and classify soil. Organic matter makes the soil darker and may be gray or dark black or dark brown. So you see that the organic matter usually it's derived from living organisms, dead living organisms, and they have a strong influence on the color of the soil. So the mineral element produce range of colors, particularly the oxides of manganese and iron. Wherever you have iron, you tend to have red, brown, or reddish brown, brown, yellow, or yellowish color. Iron oxide adds a greenish or bluish tint um, to the soil because of the what? Oxidation. So when iron 2 move from iron 2 to iron 3, which is basically rust, and you know the color of rice is darker, this tend to affect the color of the soil. So the major contributing factor, so far as the soil color is concerned, is the organic matter, then the mineral elements component of the soil. So the aeration and weathering status of the environment also influence the color of the soil. Where you have more air entering the soil, of course, you may have a problem of oxidation. You have minerals moving from lower oxide to higher oxide. For example, iron 2 will change from iron 2 to iron 3. And this will affect the color of the soil. Thus, under poor drainage or reducing conditions, some mineral may be dark gray, but well drained soil, they are oxidized. So this, where you have oxidation, obviously the color of the soil will be affected. Many tropical soils tend to have high level of iron 3 oxide, but well drained and well drained soils tend to have reddish color. And this particularly so because when you have well drained soil, this component usually exists as iron what? Iron 2. But in poor drained soils, you tend to have high level of this iron 3 oxides. And that iron 3 oxide usually has color and it tends to manage color, it tends to influence the color of the soil. So highly hydrated ions are yellow, but when I say hydrated, it means that it contains some amount of water. Yellow, but as hydration diminishes, meaning that when they lose the element loses the water component, it is replaced by what red color or blue color, and this affects the final color of the soil. Then another component that we need to look at, which is also important, is the soil temperature. In the tropics, soil temperature varies from 28 degrees to about 40 degrees on the surface. Of course, the room temperature is usually around 28 degrees. So when you move down a little bit from the surface of the soil, you may encounter the soil temperature around 28 degrees. On the surface during the afternoon, we may have a soil temperature rising up to around 45 degrees Celsius. And in the semi-arid conditions, or in the Sahel region, the soil temperature usually over around us, 45 degrees during the day. But in the night, you have temperature depression because in the Sahel region, the desert environment, you have low cloud formation. So the surface temperature or the albedo dynamics of material give out energy very fast, and so by so doing they cool down. So during the night, the temperature of the soils in those regions go down. But in the afternoon, it can rise above this 45 degrees that we've mentioned. So soil temperature has profound influence on the biochemical and physical processes of the soil because the temperature also influences the soil formation processes. Expansion and contraction leads to a break-off of soils, break-off of soil rocks or it flicks rocks so that finally they are disintegrated into soil particles. So there's bits of the lecture we are done with it. So let's take the second slide and then we move on. So let me see. However, let me upload this into your WhatsApp platform. Yeah, let's see. So let's before I continue, let me ask whether you want to there are any questions. If we don't have any questions, then I move on. So let's say organic component of the soil. Let's talk about this. How many slides? We have about 46 slides. When we are done with it, we close for today. So let's start from here. Organic component of the soil, or organisms of the soil. So organic matter is what the non-mineral portion of the soil solid, and as I said earlier, usually it's generated from other animal or plant remain, and the microbes and in the soil also contribute to the organic matter of the soil. So it comprises the residues and remains of the higher plants, animal life, together with soil microorganisms such as bacteria, fungi, and actinomycetes, then protozoa and nematodes, and algae. These are the sources of organic matter in the soil. And usually we tend to overlook this microorganism. They play a major role in the fertility of the soil. We only focus on the things that we can see. But then what we can't see play with our naked, what we can see with our naked eye play a major role in ensuring that the soil is fertile. Chemically, soil organic matter contains various forms of carbohydrates. So if you see organic matter, because it is generated primarily from the major proportion is from plant source, and the structure of plants usually contain carbohydrates, and carbohydrate consists of sugar, starch, hemicellulose, and cellulose, and these are all structures from plant. Then we can also mention fats, waxes, lignin, and then protein. So chemically, these are the nature of the various organic matter that we have. So the composition of plants and animal residues and the recycling of their nutrients is called mineralization. So meaning that when plant or animal dies and it decomposes, and then as a result of the decomposition processes, the various elemental constituents of the animal or the plant is released into the soil. Then we have what we call mineralization. There are situations where we have another concept called immobilization, whereby when you add a plant material, or basically plant material with high level of lignin, instead of microorganisms breaking down the plant material into its component, they rather take up nutrients from the soil. So they immobilize the nutrients, because they was in order to help them to decompose the plant material. And most of in agriculture, that is not helpful. So usually when we want to apply organic material to the soil, we look at the levels of this particular element, lignin. If you have higher level of lignin, if you don't in the plant material, if you don't take care, you may have nutrient immobilization instead of mineralization. So the incorporation of soil nutrient and carbon into microbial cell is called immobilization, as I said earlier on. So instead of the microorganism breaking down the organic material, they rather take up the nutrients and use them. And this is not good for agriculture. So most often, it's usually better for you to incorporate leguminous plants into as a green manure, or you can convert them into compost, because Leguminous plants tend to have high level of nitrogen, and nitrogen is very essential, and that will haste what mineralization. But when the plant contains high level of lignin, the microorganism will therefore take the nutrient, develop the limited nutrient in the soil, and use it to develop themselves. So let's talk about bacteria. Bacteria are what? A simple, when it's singular, we call it bacterium. So bacteria are simple single cell organisms. Most are spherical, rod shaped, or spiral. When we say spiral, they have a shape like a spring. Then they they have almost unlimited capacity to increase in number and multiply very fast, meaning that they're able to divide very fast into small units. So they multiply very fast. If you have one microorganism at time 0, by time t, they are more than thousands, because they are able to cell division in micro and bacteria is very, very, very fast. And so they are able to multiply and their population will increase within a short time. They are classified as aerobic, meaning that they require oxygen to survive, or anaerobic, meaning that they don't need oxygen. So, and most of the reduction of organic and inorganic, they depend on organic source. Like if you have iron rain, they can take the oxygen in the iron and survive without taking the oxygen from the atmosphere. Some microorganisms have that adaptation to source from oxygen from other sources rather than from the atmosphere. And such microorganisms can dwell very well in inert environment with high concentration of CO2. They can survive. Others cannot. Others require oxygen in order to survive. And most often, the anaerobic microbes are able to cause a process we call fermentation. They cause fermentation. If they are dealing with organic material, they can cause fermentation in the process. And that's by so they produce alcohol. So on the basis of their energy sources, soil bacteria are classified as well autotrophic, meaning that they obtain energy from the oxidation of mineral constituents such as ammonium, sulfur, iron, and most of their carbon from carbon dioxide. So then we have the heterotrophic. They follow the same classification as we have in mammals. Autotrophs are most often, if you are dealing with plants, meaning that some of the plants are, what do you call it? We usually describe plants as autotroph because they can produce their own energy. Then heterotroph, they obtain energy and carbon directly from soil, organic matter. They have to depend on other living organisms for their energy source. So this is the broad classification. And within that broad classification, if you study microbiology, you have a wide range of other classifications. For the purposes of this course, we have to limit ourselves to these two broad classifications. So then we have what they call, one of the things that we always talk about in agriculture is the they talk about the kind of relationship between microorganisms and other plants. Symbiotic, for example, we have the rhizobium in the root nodules of legume like granite, cowpea, your pigeon pea, and the rest. Then we have non-symbiotic. There's Azotobacter. These are free living microorganisms. As Azotobacter species, they're microstudium species. And most of them symbiotic, we are more interested in those that can fix nitrogen. The non-symbiotic nitrogen fixers are heterotrophic. They are heterotrophic in nature, meaning that they need to get energy from other sources. Then there's symbiotic, so we say symbiotic usually from an association said that the benefit from the plants, either the plant offer them protection, then they in turn will convert the atmospheric nitrogen into nitrates and make it available to the plants to survive in the tropics. I always say that in my class, it is universally accepted that in the tropics, phosphorus and nitrogen are usually deficient in the tropical soils. So most often, we need to capitalize on some of these associations to improve the soil fertility in order to make available essential nutrients to plants. So bacteria that oxidize ammonium ions. Please, I will ask questions on this. Is one of my favorite area that I usually ask questions. Bacteria that oxidize ammonium ions to nitrates. A good example is nitrosominal species. And those oxidize nitrites to nitrate. A good example is Nitrobacter. They are all autotrophic in nature. So you see that, and plants are able to utilize, some plants are able to utilize only this nitrate. Others, few plants are able to use ammonium ions. So most often, if it's in animal kingdom, sorry, in the plant kingdom, you realize that plants that depend directly on nitrates are in higher proportion than those that depend on ammonium ion. So you realize that this microorganism here are providing essential services we call ecosystem services. So if you don't handle them very well, you may not able to have nitrates available to your plants in your cropping systems. So you need to manage this what do you call it, a microorganism very well in our soil so that they can also enhance the productivity of our crops. Then we have there's a single cell thread like this particular group of plant microorganisms. Sometimes they are very difficult to describe because they behave like bacteria. Another time they behave like fungi. So we call them actinomycetes. They are single cell thread-like organism, often branched because when you say branch and tangle with aerial filament, known as mycelium. This is a classical description um, of, of fungi. So the attribute I've mentioned right now, it describes the behavior of fungi. Mycelium is the only fungi that form mycelia or mycelium. The mycelium will break up into fragments which resemble bacteria. You see that it's this group of organisms falls between bacteria and then the fungi. Sometimes we call it we describe them as being the transition between bacteria, fungi, and then of course bacteria. You find them in the soil. They are very, very useful. Then we have fungi. It is very common even in our homes when you leave your bread on your table. The black or yellowish things that most often grow on your bread or your kenke, they are fungi. Fungi range in size from microscopic but larger than bacteria and then actinomycetes. And the most often visible, there are some visible specimens such as mushroom. There are some, they are very difficult to see, but particularly yeast, mycetes. The yeast, if you don't observe them under a microscope, you may not be able to see them. And they are most dangerous component group class of fungi. But some of them are very useful in biotechnology, the mycetes that I mentioned. Then we have algae. They are the simplest green plants. You see them in your bathroom, on the wall, wet environment, you see them all over the place. Then we have the protozoa. They are single cell animals which are essentially aquatic. So in a pollution environment, you may have a lot of this protozoa. And some protozoa are very, very, very harmful. A very good example is um, malaria parasite. Plasmodium is a protozoa. Then we have a nematodes. They look like a worm. And nematodes, I am of good concern when you are dealing with plants with rhizome, combs, tuber plant like carrots. They can deform the carrot, the structure of the carrots. Then they can also deform the rhizomes in ginger and the rest. So normally when you have nematodes in the soil, they usually affect plants like cocoyam, plantains. So you have to find a way to, um, what do you call it, to treat the soil in order to get rid of nematodes. And they are very particularly troublesome in horticultural production. When you are dealing with horticultural crops, they can really be troublesome nematodes. So nitrogen fixation, we have atmospheric nitrogen is fixed by number of soil microorganisms, including fungi, then blue-green algae, and bacteria. So whether the microorganisms are very, very important. The symbiotic fixation by rhizobium species in association with legume, and the non-symbiotic fixation by azotobacter species and then Biogegraphy species are common in the tropical soils. Are very, very common in the tropical soils. Then we have what they call the mycorrhiza. Mycorrhiza is what association, and these are usual association between fungi and the root of a higher plant. What happened is that when they form this association, because of the mycelial network of fungi, the plants become very effective in mobilizing limited nutrients like phosphorus and then nitrogen in the soil. And in turn, the higher plants will give the mushroom carbohydrate to survive. So if you have any association between the plants and then higher and the fungi, we describe it as mycorrhiza. And people specialize in this type of association and capitalize on it to help plants to survive in an environment with a nutrient deficiency. Fungi obtain food material from the host, which is the higher plant, while the material act as the extension of the root system. Plants uptake of nutrients such as phosphorus is greatly enhanced by mycorrhiza association. So this is one of the important. And let me talk about association between mushroom and plant. What is the name given to association between algae and mushroom? This is please right there. You have to write this down and submit it. I don't know how they compile your continuous assessment in this program. Anyway, you can just read on it. Please find out the term for the association, the name given to the association between algae and then the fungi. Algae and the fungi. Then algae and higher plants. Try to get this, you read about them for your own consumption. Then let's look at factors affecting the rate of decay of organic matter. The decay of organic matter is influenced by optimal moisture supply, adequate aeration, and high temperatures. So these are three key factors that are necessary to hasten or decomposition of organic matter. So in absence of moisture and you have high temperature, the material becomes mummified. But in presence of moisture and, and temperature, you may have the organic material being mineralized by microorganisms. So a factor of profound importance is organic matter decomposition is the ratio of carbon to nitrogen in the soil. So if this ratio is not well balanced, that is whereby you have immobilization. As I mentioned earlier. So microorganisms involved in humus formation require nitrogen for efficient decomposition of organic material. So in whereby the material that you apply to the soil lacks nitrogen, they will take nitrogen from the soil. But then if the material you apply to the soil has high level of nitrogen, they will mineralize it. So this relationship depends on what we call carbon nitrogen ratios, or we call the CN ratio of the material. Material with the low CN ratio tend to be what? Immobilized. Becomes a precursor for immobilization of nutrient from the soil into the microorganism. So what is the importance of organic matter in the soil? One, influence on nutrient availability, because they become as a site for cation. They have what they call cation exchange capacity, exchange of nutrients between the soil and the surface of the organic matter. So reserve nutrients are normally found within the matrix of the organic matter. They also they have effect on what soil aggregation, the ability for the soil particles to come together to form clumps. And this is so the organic matter acts as a cementing material to bring the particles together. They also affect water convection or water conservation. Soil with the higher level of organic matter most often are able to conserve moisture than those with relatively low amount of organic. Then when we say organic matter acts as buffering, what it means is something is a buffer. It is the ability of that substance to resist appreciable change in our pH, a pH. So if you have high organic matter in the soil, you may also have relatively stable pH range, and that will enable the plant to survive. Because plants need a stable pH range. Some plants prefer less acidic medium, some close to neutral medium in order to survive. So organic matter acts as a buffer. So it resists the changes in the pH of the soil. So and then conversion of gaseous nitrogen. Okay, they also contribute to gaseous exchange. The inert or the intact, the component of nitrogen in the organic material, when they decompose, some of them are released as nitrogen. Some organic material serve as reserve, and some act as carbon stocks, take large amount of CO2 from the atmosphere and store them within the soil. So if whereby you have too much of it becomes an issue, they become a source of plant diseases, particularly fungi, because fungi can inhabit the surfaces of organic material, and so they produce spores that can infect plants that are living by. So these are very, very, very important. So then let's look at the factors that can affect the level of soil organic. Climate is one of them, type of vegetation, topography, soil parent material, and the time. So these are factors that can affect the level of soil organic matter. Climate, you can talk about temperature and rainfall. You need temperature and rainfall to hasten decomposition. So in tropics, we tend to lose a lot of organic material very, very fast because of the high temperature and high amount of rainfall. Then the type of vegetation in the forest zone, the soils tend to have high level of organic material because of the leaf litter that comes from the trees, unlike grassland. In the grassland, because of the nature of the vegetation, the level of organic material in the soil from plants is very, very low. And in the topography, it's expected that on the top of the mountains, we have experienced low levels of organic material as compared to the base of that mountain. Then the soil parent material is very, very important. What is the nature of the parent material? Is it granite? Is it sedimentary rock? Is it a metamorphic rock? All these factors will contribute to the level of soil organic matter in the soil. Time, it's expected over a long time, long run, the level of organic matter material in the soil should go down if it's not replenished by other sources like the vegetation. Then the levels will virtually diminish over time. Now let's look at one of the important components of soil. We call the soil reaction, acidity, then alkalinity of the soil. The whole soil chemistry is centered on those two key factors: acidity, then alkalinity. There's a concept we call soil colloids. That's the most active portion of the soil, and usually it consists of clay fraction or humus component of the soil. I said earlier on that the humus play that role, and that role enables the two component clay to have what they call the cation capacity, ability to absorb and release cation into the soil. So clay particles are fine plate-like crystal unit, and hydrous oxide clay or hydrous oxide of iron and aluminum, example gibbsite, and the limonite tend to have tend to have high cation capacity. The clay missiles, when we say missile, the missiles are like this. So these are particles of clay particle, the structure of the clay particles. And you realize that the cation that we are talking about is this. Because the surface of the clay particle is negative, it is able to attract excess cations in the soil and store them on their surfaces. So when the pH of the soil changes, some of this is released to replenish whatever that we have in the soil and make it available to the plant. So most of the soil chemical reaction takes place on the surface of the soil, of the clay particle, or the missile of the clay. So this is a classical structure of clay particles. Of course, if you take organic matter, they also have similar charges on their surfaces, and these charges are able to attract excess cation within the soil and act as a reservoir. When the need comes, then they release them into the soil. So organic soil colloids, the complex humus particle on the missile or the unit, or say the unit is a missile, is made up of CHO, that is carbon, hydrogen, and oxygen, rather than silicon, aluminum, and oxygen, as in silicate and anhydrous clay. So the basic difference between the organic and then inorganic, the organic is usually coming from humus. The inorganic is coming from other clay particles. Rather, the main component or the constituents are carbon, hydrogen, and oxygen in the case of humus. Then, in the case of inorganic, you have silicon, aluminum, and oxygen as the backbone of the colored material. So humus particles or humus particle is very fine, amorphous, and not crystalline. When we say something is amorphous, it means that it has no shape. You know, it usually takes the shape of the whatever container you put them in. It has no shape. But then when you look at the inorganic colloids, they have shapes. They have shapes, so they are not amorphous. And many of them are crystalline in nature, but humus is not. So let's say the cation absorptive capacity of humus is far exceed that of multimoronite. Multimoronite is a type of black clay that in Ghana you can find them in Akuse. We call them Akuse series. They are black in nature, very, very fertile. But then they have a problem because of the way they are. They're so plastic. When they are wet, they are very difficult to work with. When they are dry, they crack. You know, you see them, they have a whole lot of crack in them. But then because of their nature, you have to do a lot of interventions in order to use them for agricultural purposes. So humus is not as stable as clay, and so it's formed and destroyed much more rapidly than the latter. Okay, so humus is not stable. You know, clay particles are more or less, because they are inorganic in nature, they are able to stay in the soil for a very long time as compared to humus. Humus, the level can change depending on the environmental factors. So let's talk about cation exchange capacity. The minute silicate clay colloid particle ordinarily carries a negative, as I said, if you look at the diagram, whether they have negative charge and attract thousands of positively charged ions. So the ability to attract and release ion is sometimes described as the cation exchange capacity of the soil. And this depends on the amount of clay material you have, and of course, organic material that you have in the soil. So you realize that organic and the clay component of the soil, they are very, very important to ensure fertility of the soil. So the absorption is just like absorbing, but in first soil science we say absorption of cation by colloid, meso, organic or inorganic, result in the release of one or more ions held by the meso, and thus is described as what exchange capacity. So cation exchange and plant nutrient availability, there are two important factors involved in the availability of plant nutrients. The first one is the total amount of nutrient available to the plant as exchangeable cation. The second is the degree to which this exchangeable complex is saturated with base rather than hydrogen. So the more hydrogen you have, the hydrogen ions are able to bind, because of their small size, they're able to bind this, to the surface of the clay particles. And when they do that, they will prevent other cations from getting access to the surface of the meso. And this only happens when the pH of the soil is very, very low. At the low pH, you have lot of hydrogen ions, free mobile hydrogen ions moving all over the place. So normally they will occupy the micelles because the surface of the micelles are negative and hydrogen ions are positive. So negative and positive ion attract. Then because of the small nature of the small size of hydrogen ion, they are effectively able to combine or bind with the surface of the micelle and displacing ions like magnesium, potassium, what do you call this one? Yeah, potassium and sodium, the rest, because of their sizes. So they have low radius to charge ratio, low size to charge ratio, so they are able to bind effectively on the surface of the micelle. Then how do we measure this? We have a concept we call percentage base saturation. The percentage of the cation exchange capacity by exchangeable base is called percentage base saturation. So if you want to measure the level of this bases on the surface of the soil micelle or clay micelles or colloid micelle, we use a concept we call percentage base saturation. So, and this is measured as what? Exchangeable base divided by cation exchange capacity times 100. Of course, nobody is going to ask you questions on this. But if you do understand the principles behind this, how it's being used in agriculture or in other discipline, it will be helpful. So when you have time, please read on this, or what is percentage based saturation, what is it application in agriculture, what is it application in land restoration. So please, so soil reaction or pH or soil acidity. The acid soil is one which pH, an acid soil is one which the pH is less than 7.0. The hydrogen concentration of the soil is higher than that of hydroxyl ion. So if you have more of hydrogen plus ion in the soil, then meaning that you are dealing with the acid soil. Conversely, if you have hydroxyl ion in high concentration, then the soil can be described as being alkaline. So let's look at soil acidity is caused by any of the following factors. One, organic and inorganic acid released during organic matter decomposition. Of course, one of the key organic acid, which is very common, is the ethanoic acid. It's very, very common, and normally it's associated with decomposition, and this is released into the soil. Then inorganic acids sometimes come from the application of fertilizers, acid-based fertilizers. They contribute to acidity of the soil. And leaching leads to loss of exchangeable base through percolation and drainage. So wherever you have high rainfall conditions, you may have leaching. And when you have high leaching in the soil, you also experience low pH and the soil becomes acidic. Application of certain nitrogenous fertilizer, notably ammonium sulfate, can contribute to acidity. If you want to reduce acidity of the soil, then you need to apply lime. And lime will reduce increase the acidity of, increase the pH, from the acid rain to more or less alkaline rain. So we finished with lecture 10. So let's move on to 11. Of course, let's see what we have here. Maybe then let me pause. If there are questions, then I move on. I don't know whether I'm still online. Am I still online?
You are still online.
Okay, good. So let me pause for 5 minutes, then we come back to continue with the lecture. What is it? Is it 11 or so? So please just give me a moment. I'll be with you. Okay, so let's continue with the lecture. Let's see where I am. So let me go back to the presentation mode. So let's look at structure and related properties of water. Everything that happens within the soil depends on the water, the movement of water. Water is a solvent and carries a lot of um, dissolvable material through the pores of the soil, and most of the soil reactions depends on this amount of soil that you have. So water is a simple compound. I think from your basic chemistry, its individual molecules contain one hydrogen and two much smaller hydrogen, one oxygen, and then two smaller hydrogen atoms. So the elements are bonded together covalently, each portion sharing a single electron with oxygen. And the resulting molecule is not symmetrical. It's not symmetrical. The atoms are not arranged linearly like this. You say because there is a lone, what they call the lone pair somewhere here. And that lone pair will repel this hydrogen bonded to the oxygen. So you realize that it has some kind of a triangular shape as we go along, you see it, or V shape. Instead of hydrogen atoms, instead the hydrogen atoms are attached to the oxygen in a sort of vein arrangement and separated from each other by an angle of 150 degrees. So let's see. So this is our water structure of water molecule. And then because there is a lone pair of electron here, meaning that a pair of electron at the top here, this push, it repels those hydrogen down and this one down. And because of this lone pair, you realize that the structure of the water molecule, um, the electrons here are drawn more or less towards the oxygen more than the hydrogen. The hydrogen has only one electron, but this one electron spend more time with the oxygen. And as a result of that, it developed what we call partial positive on these two um, hydrogen atoms. Then the oxygen will develop what? A partial negative. Now, how does affect water is that you realize that because of this structure, the molecules of water is able to form combine like a chain, combine like a chain. So the negative end here will now connect with another oxygen, another hydrogen water molecule to form a network. And this is very important when it comes to freezing of water. And as a result of that, when water freezes, you realize it still sits on the top. You have water, when a lake or river freezes, you have the ice on top. There's some amount of water down there to enable a living organism to survive in the freezing water. And this structure also enables the water to adhere to surfaces, to wet surfaces. And of course, it also enables water to move through pores of the soil. So let's move on. So polarity of water, the property of polarity, as I mentioned, this is the polarity that we are talking about. There's positive and negative charges that we have on water molecule. The polarity of water, the property of polarity helps explain how water molecules relate to each other. Each water molecule does not act completely independently, but rather is coupled with other neighbor molecules. The hydrogen or positive end of one molecule attracts the oxygen end of another, resulting in what? Polymeric, a polymer-like grouping, as I said earlier on. So we may have something like this. So if you look at this diagram, this bit is what one water molecule. This is another water molecule. This is another water molecule. And you realize that the hydrogens here, they all have a partially positive charge. But on the surface of this oxygen is negative charge. So meaning that this hydrogen can combine or attract the oxygen in this water molecule. And they form a bond, what we call the hydrogen bond. The hydrogen bond. And this hydrogen bond influences the physical property of water. So you realize that it affects the boiling point of water. The more hydrogen bond that you have in a liquid, it means that the higher the temperature at which it can boil. If you take alcohol has low hydrogen bond, so around 70 degrees Celsius, it escapes into what? A vapor. It boils. By the case of water, the temperature, the boiling point of water is almost around 100 degrees Celsius. So this is hydrogen bond. So we have hydrogen bond between the molecules. Then we have covalent bond within the elemental nitrogen and the oxygen. So this is the basic structure. And this helps water to form crystal-like structures when it freezes. And it also enables it to stay on the liquid water and allow living organisms in the water to survive. And you realize that when the freezing water has low density than the liquid water, so that the freezing water is able to sit on the liquid water. And this physical property is very unique to water, and it's one of those things, mysteries that we sometimes find it difficult to understand. Why God in His own wisdom made water so that um, what they call living organisms in the cold environment will always survive. Particularly fish and aquatic mammals can survive during the winter. So let's look at so hydrogen bonding, the phenomenon by which hydrogen atom act as connecting linkage between water molecule is called hydrogen bonding. This is relatively low energy coupling in which hydrogen atoms are bonded spontaneously to different molecules, as I indicated in this diagram. So hydrogen bonding suggests two basic forces which account for water retention and movement in soil. One is the attraction of molecules to each other, what we call cohesion. The other is attraction of water molecule for surfaces, we call the adhesion. So, and this phenomenon, these two phenomena contribute to a membrane-like surface of water and enable insects to actually move on the surface of the water. So when you pour water into a cylinder tube, you realize that you have a meniscus that is curved inward. It's as a result of these dynamics of cohesion and adhesion forces in the water. So, and it also contributes to what is termed as surface tension. So you have something like a membrane-like material. The surface of the water behave like a membrane, so that enable insects, some insects, to walk freely on the surface. So the net effect of inward forces like cohesion and adhesion at the surface cause water to behave as if its surface were covered with what? Stretched elastic membrane. This is called what? Surface tension. And this surface tension is very, very important. It helps water to move up plants. It also helps water to move through soil. Capillary actions of water, hydroscopic movement of water depend on this so-called phenomenon of adhesion and cohesion. Of course, as another contributing factor of surface tension. So water, soil-water relationship, we have what we call maximum water retentive capacity, maximum water retentive capacity, the ability of the soil to hold water. So if you have micro and micropores, when they are filled with water, the soil is said to be water saturated, meaning that when you have the micropores, that these are small pores, then the micropores, when they are all filled with water, it means that there is no space for air to more or less occupy. Then we have what we call maximum water retentive capacity, and that is not good for plants. Then we have filled moisture capacity. In this case, the micropores are filled with water, then the macropores are filled with gases. So you have a balance here. You have a little bit of gas and water within the soil, and that's very good for plants to survive. Then we have the voting coefficient of the soil. When the soil is so deficient with moisture to the extent that you have the plants showing signs of drooping during the day. Sometimes during the day they will appear as if they are dying, but during the night they will recover. But then if they remain drooped or wilt throughout the day and the night, then at that point, it means that the water level is at what they call voting coefficient of the soil. If the water, the plant is not able to recover during the night, then the amount of moisture in the soil is described as the voting coefficient of the soil. Then we have hygroscopic coefficient. This water is unavailable as liquid, and they exist as well in a moisture, or what they call it, vapor, in the pores. So they are unavailable to the plant. So the plant cannot use this type of water. So how do we conserve moisture? how do you conserve moisture in the soil? The first one is mulch. And what are mulches? When you deliberately, mulches, we can have a synthetic and natural material. If you use a black polythene sheet to cover the surface of the soil with the objective one to conserve water and of course to control it. So when in the horticulture industry, you realize that the farmers will cover when they plow, then when they finish plowing their land, they cover the surface of the soil with black polythene sheets, and that is a mulch. But this particular mulch is synthetic mulch, and the function is because of the black nature. Black materials are able to absorb radiant energy, and they can kill off microorganisms such as nematodes, then also control weeds, then conserve moisture. However, you can also use plant material as mulch around the base of the plant. Particularly in yam production, they create something like I don't know how to describe it. They use weeds to create something like a headgear, and they put it on top of the mounds in order to conserve moisture. And if you want to control water losses, one of the things that you also have to do is a runoff control. And runoff control can come in so many forms. You can either geoengineer good drainage systems, construct barriers to reduce the rate of runoff on your soil. And then the systems that you put in place in terms of plumbing, the type of plumbing approach can also reduce the runoff. Then we have another concept we call the contour plumbing. I'll show you pictures of contour plumbing. And then we have a terracing. Terracing, if you are in a hilly area, like a Nepal, you are in Amadefair and the rest, and want to cultivate on the surface on the slopes of the mountain, you have to use terracing, as that will contribute to erosion. Then we have a strip cropping. You plant your crop in alternative band. You have groundnut here as one band, maybe sorghum another band, cassava or maize as another band, and that reduces the amount of water runoff. Then you also need a tillage or weed control. Tillage or weed control. And normally people prescribe what they call zero tillage, and weed control reduces evapotranspiration because the weeds will also absorb moisture and then release water from the soil and release us in the form of a moisture through transpiration. So then you use fallow, meaning that you don't plow or till the land. You allow the plant to grow and then the field to grow back to its original state. And this can also conserve. So this is an example of what they call terracing. You the hilly surface. You have steps. They've planted in the form of steps from the top to the bottom. So what it means is that when there's a runoff, it gets to this one, that one, slowly before it gets to the bottom. And by so you reduce erosion. Because the water stays at each band for some time, it speculates into the soil. And this reduces soil erosion. So this is what we call this strip cropping. You see that they've planted the crop in the form of bands. Isn't it? So there's a strip cropping region. You rather have oats here. The oats, these are all oats. Then the green part here is corn. Then you have hay. The hay is normally used as a fodder to feed animals. So they'll cut this and use it to feed the animal. Oats, it's normally we all enjoy oats as our breakfast. Or then corn is in between. Then this is what is termed a contour plowing. You see that instead of plowing like this, they've the operators design the applying system in a way of as a band. And if you do contour plowing, if water is moving from the top to the bottom, the speed of the water is reduced. And by so if the water flows slowly to the bottom, test part or greater proportion can then get into the soil. So this is contour plowing. Now, how do we conserve soil? Soil erosion and conservation methods. Soil erosion, there are two basic types of erosion. We have geological and accelerated. The geological, you can't do anything about it. The geological erosion lead to formation of all kinds of landforms. What do you call it? Canyons and mountains here and there, peaks. There's nothing you can do about it. But this part is what most of we contribute to as human, and we have control over this. That's the rated one. So geological erosion is that will take place under natural conditions, and you can't do anything about it. Water erosion is one of the most common of all geological phenomena. It accounts in large parts for the leveling of our mountains and development of plains, plateaus, valleys, river flats, and deltas. So you realize that the geological erosion, they are very, very important in contributing to land forms. So let's see how, then we also have, so the vast deposits that now appear as sedimentary rock originated in this way. So when they just scoop part of soil material and lay them in layers, over a period of time, the pressure and then cementation process will lead to the formation of sedimentary rocks. So they are very, very important in nature. So geological erosion, you can't do anything about it. Then the two types, when it comes to processes of erosion, two types are recognized in accelerated erosion. The first process is detachment or losing influence, which is preparatory action. So what it means that the agent of erosion will detach. Either it's rain, you have what they call splash. The water molecule will hit the soil and dislodge the soil particle. So that is detachment. Then the water then transports the detached particle from one point to another. And this can be done by floating, rolling, dragging, or splashing. Then we have what they call the causes and rate of accelerated erosion. Rate of erosion, we normally, is a universal way of measuring how fast erosion is taking place at a particular location. So we have what called the universal soil loss equation. And this identifies the factors on erosion losses. And this equation is expressed as this. So we have erosion being as a function of R, K, L, L, CP. Let's define this term. Where A is the computed soil loss per unit area. R is what? Rainfall. So then we have K is the ability of the soil to resist detachment. So we call it soil readability. You realize that some soil are so resistant to detachment, and as a result of that, the rate of erosion with that type of soil is very, very low. Then we also have this component called the slope. The steepy, on the flat plains, erosion is very, very low. On this steepy slopes, you have erosion being very, very effective. Then we also have X, that is, we talk about the slope length. So these factors, slope length and slope gradient, act in tandem. If there's a steepy, if the slope is very steep and short, meaning erosion, the effect of erosion will vary. But if it's steepy and very long, what do you call it, slope, then it means that the impact of erosion will be very, very, very high. So these two factors, length, then the gradient, acts together to influence soil erosion. Then the crop management, and this bit we can, if you don't manage your crop system very well, vegetation cover is very, very important. You can go into what is called agroforestry systems, planting trees around maybe your field can also in a way reduce the um, soil erosion. And when you harvest your maize or your plant, just leave the what they call the stoop or the leftover material on the farm. Don't burn them. If they are there, they will act as a mulch and prevent erosion. Okay. Then erosion control practices. What are the measures the farmer, whoever, put in place to reduce erosion? So all these factors can contribute to what you call soil loss per a unit area or erosion of soil material in a particular location. So types of erosion, we have the sheet erosion. Soil is removed more or less uniformly from every part of the slope. So this is a picture of uh, sheet erosion. And so when sheet erosion is taking place, if you don't take care, you may not see it. Before you realize the root systems of the plant or your foundation is up because the soil is, removed in layers. You may not see that erosion is taking place. Then we have gully. This is the most dangerous one. Develops when water flow in small canals, and enlarge, causing cutting and abrasion, and often leading to considerable damage to both topsoil and subsoil. So you realize that gully erosion, that is what you see. And that's if you have this problem and you want to address it, you need to do geoengineering. You have to bring in heavy machinery to cover up this hole, or you transport soil from somewhere to fill the hole. Then you try and then reclaim the land. If you don't do that, you can't do it. So this gully erosion can cause considerable economic damage to the environment because you need money to bring this land back to its original form. Then we have real erosion. It's open up as a small channel. So if you don't control this, it leads to this one here. If you don't control it, it leads to this. So many gully erosion start as a real erosion. So it's open up small channels on the surface of the soil, and if you don't control at this stage, if you don't find a way to control it, it will lead to gully erosion. Then the next bit is the so-called splash. And you realize that you mentioned detachment. You realize that the droplets of water will dislodge the soil particles. So that is the initial stage of erosion. So detachment, then you see the water here then carried off the particle along. So every erosion starts in this form. So then this will either open up the surface like this or carry the material in the form of a sheet. So if there's no intervention, then you may have a gully erosion. Then another form of wind erosion, which is very common. Another form of erosion is wind erosion, is very common in the arid region. Wind erosion is the transportation of soil particles by wind, and most often the particle is used as a tool. I call it abrasion. You use it to attack the surfaces of hard rock. So this is essentially this is essentially a dry climate phenomenon, and it occurs in areas like Sahel region in the desert environment. So you may have it in purely arid or semi-arid environment. Wind erosion is very, very important there. So you realize that just as I said, abrasion, the wind will use the particles that it is carrying as a abrasive tool to construct structures like this, to attack the surfaces of rock, carve them into landforms like this. And it's very realize that this is the bottom of the if you look at the structure, the actual base is somewhere here, but then the wind uses the particle that it is carrying as tool to carry off the surface of the rock. So you end up having a structure like this. And then the position, they carry the material and they deposit them and leading to formation of sand dunes. So the sand dunes are primarily deposition. The soil particles are picked from somewhere and then deposit them at one location. So, and you can also create a sandstone or dust storm. And this is very, very common in the Sahara regions. Along Saudi Arabia, even Dubai, they tend to have this problem, sandy storm or dust storm. Erosion control, how do you control it? You can plant vegetation, you use mechanical control measures where you do engineering. Um, so these are the key things that we can do. Vegetation management, you use it when you have a wind as an agent. You can you plant trees as a windbreaks, or if it's water, you can have cover crops. Then mechanical controls, creating a drainage systems in a way that it's control the flow of the water on the surface, and by so doing you reduce the erosion. So please, when you have time, read more about erosion control on your own. So on that note, I think we are left with one lecture, but I'm not sure I'm going to continue. I have to call off today's lecture. I look as if I swear, let me see, it's almost 9:13. Um, so I have to pause here. Then please, I'll, so we have the one more lecture to complete, and we are done. That talks about soil types of the soil types and distribution in Ghana, and it also educates. It has a practical application. What kind of crops that you can plant in each geographical location in Ghana, and this has to do with the kind of soils that we have. So we need to look at that. Uh, uh, Maybe I don't know next week. Please, can you sacrifice 2 hours somewhere next week? Then we finish with this.
Yes, sir.
Yeah. So, Elijah, so you discuss it with your colleagues and you get back to me on the platform. It's just 2 hours. Then we are done with this. However, I will send you the slide. Then other reading material. I think I have a comprehensive handout which I prepare for code. So I'll look for it and forward it to you. I don't know whether I've done that. So I'll send it to you. And in that, what do you call it, manual, you have all the lecture notes covering the course. And it has been designed in a way that you can read it on your own. Then when you do so, you answer the questions because sometimes when I'm becoming so lazy, I just pick them up and combine them as my end of semester. However, I'll send you also my past questions for you to look at how I set my questions. Okay. So I'll do that. I'll send the code handout to you. Then for the questions, maybe next week, or I'll do that in the course of time, maybe, because I have to search. I have to go into my archives and look for them. So, yeah. So thank you very much for coming. Bye bye. See you there.
Please, colleagues, please don't go. Our cell is moving. Let's take the decision right now. Please, colleagues, open your microphones and let's talk. So when are we meeting the lecture, please?
Friday 6 p.m.
In the evening?
Yes.
Yes,
6
6 p.m. That
Anyone?
is in the evening. Yeah,
p.m.
p.m. evening as
The time
usual.
that you 6 p.m.
Okay, Friday 6 p.m. Okay.
Yeah,
Then
Uh-huh.
you ask, can you make it 6 in the morning?
yeah.
Madam Vanny, you like trouble. Okay. So as we have decided, um, Madam Vanny, do you have his number?
I have
So
his
that
number.
so that we can communicate it to him right away.
Okay.
So that we can say Friday. We said we meet him Friday in the evening. So Mr. Nyame, please do that for me.
Yeah, I'll do that.
Okay. Okay. Thank you. So on this note, I think we can take our time and go back to our churches small and then come back around 11 for the next lecture.
But is he not down for today?
But we have another lecture or it's done for
Yeah,
today.
that will be 11:30 or yeah.
That's what I was saying that we are going to church, but we have to return around 11 to. Uh,
Yeah, yeah, yeah. Okay.
okay. So on this note, I'll bid you goodbye.